book. The geological control of groundwater, the classification of rock, and reference to their water-bearing property have been discussed. The unit also describes the occurrence of groundwater in the different geological terrains of India. Finally, there is law and its validity. The determination of hydraulic conductivity and groundwater traces has been touched upon. So we'll start this with Unit 9, that Introduction to Oceanography. ତାହାର ମ୍ୟୁଟ୍ ପୁଷ୍ପପ୍ରିୟା ତମେ ଟିକେ ମ୍ୟୁଟ୍ କରିଦେଲ ନିଜକୁ ଥ୍ୟାଙ୍କ ୟୁ
ଆଜ୍ଞା
ଟିକେ ମ୍ୟୁଟ୍ କରିଦିଅ ତମେ ଇକୋ ଆସୁଛି ତ ଓକେ ଥ୍ୟାଙ୍କ ୟୁ The earth is divided into several plates. Each plate has two parts, continental and oceanic. The continental section comprises the land segment. It may be subdivided in continental shelf, slope, rise. On the shelf, one finds remnant topography features of land that have submerged because of sea level rise. The deep region of the ocean comprises ocean plate. These regions have formed because of generation of new ocean at the convergent or a divergent boundary. During the antecedent cold climate phase over the earth, a sizable amount of water got locked in the ice sheet and in the glacier, and this has reduced the level and spatial extension of the ocean. The plate tectonic determines the arrangement of continents and ocean and plays a vital role in destruction or expansion of the ocean. The new plate has a very young age at the mid-oceanic ridge, and it becomes older in the region that have drifted away. The sedimentation over the ocean is regulated by the supply of detritus from the rivers, wind, and from the biological productivity. Slumping supply sediments over the rise, the oceanic plate receives a negligible amount of sediments from land. The chemical and physical processes regulate biogeochemical cycle of the ocean. The ocean has a layered structure. The density of seawater increases with depth. The salinity of the seawater decline in halohaline. Temperature decreases in thermocline. The physical, chemical, and biological property of the ocean are described to provide a glimpse of the influence of these on the process of Earth that regulate the global climate. So the physiography of ocean. The Earth has formed as a molten mass of gases billions of years ago. The cooling of the Earth has released gases and water vapor, and that has formed the atmosphere and water above the globe. It is believed that during the formation of the core, mantle, and crust of the Earth, the water has migrated from the deeper region of the Earth to the crust. About 96% of the water on the globe is stored in the ocean, and it has a horizontal extent of several hundred kilometers. Ocean covers about 71% area of the globe. It has a variable vertical extent. The physiography of the ocean is therefore very important because it determines the quantity of water that can be stored in the ocean. Exchange of water from the ocean to the other reservoirs determine the extent of submergence of the continental margin under the ocean. Physiography subdivision of ocean. The physiography of the ocean is regulated by the ongoing geologic process of the earth. The most of the ocean is very young compared to the age of the earth. It is because of the ocean is created at the divergent center and it is consumed at the convergent center. The continued destruction of the ocean and reorganization of the continent have reshaped the ocean. The present reorganization of the continent started with the breakup Pangea and the supercontinent. The ocean crust therefore does not have older than 200 million years. The physiographic feature of the ocean therefore vary over the time. Subdivision of the ocean. The submerged region of the continents is classified as continental margin, while the oceanic crust that has formed due to the tectonic processes at the divergent boundary is known as oceanic region. The tectonic and the hydrological processes have shaped the physiographic features present on the floor. Based on the process of this formation and extent of submergence, the margin of the ocean may be subdivided into two distinct categories. So the margin of the ocean that has been divided into two different categories. There are the continental and oceanic margin. The continental margin is the portion of the existing continent that is now submerged in the sea. It essentially is the land region that has a low density being produced by the volcanogenic processes. The density of the oceanic plate is 2.9 gram per centimeter cube. The continental section has a thickness of several kilometers, while the oceanic plate is very thin. The region, the continental margin of ocean. The region comprises three main zones: continental shelf, continental slope, and continental rise. Adjacent to the land ocean boundary, the submerged shallow flat region of the continent is termed as shelf region. The spatial extent of the region is highly variable. It varies from few to several hundred kilometers depending upon the tectonic setting of the region. Generally, for the active margin, the spatial extent of the continental margin is very short. For example, the continental margin of the state of California, USA is only 1 kilometer. The subdivision of the ocean is shown by this figure here. Land, self break, then slope, then rise, then the mid-oceanic ridge, how it has been formed. With Because of the shelf in an extension of the continental landmass, it has all the physiographic features of land. Even though not visible, the shelf has small hills, basins, and the remnants of the channels of old rivers that were flowing over the shelf when it was subarically exposed. We must remember that the shelf is the region of the earth that has periodically submerged or has been aerially exposed depending upon the regression transition of the sea in the response to a change in earth climate. The earth has experienced several regression and transition cycles. The most recent is 20 kilos years old. It has been achieved that about 20K years back, the global sea level was about 120 meters less than the present level of the sea. At such a time, land-bound sea and land boundary was about 60 to 100 kilometers on oceanward. One may note that at that time the present shelf was exposed land and it was not part of the sea. Size of the ocean on the globe was therefore reduced during this period. As the sea level has gradually increased during the past 14.5K years, the shore has migrated towards the land and has submerged considerable amount of land. This has shifted the shoreline and the mouth of the rivers inland. If one explores the shelf region by the underwater sensor, one will discover many buried channels of rivers on the shelf. The channels of old rivers are manifestation of antecedent sea level. The east and the west coast of India has a passive margin. The width of the shelf along the east and the west coast of India is highly variable. The west coast has a much wider shelf in the northern region that extends to some 300 kilometers in the Bombay offshore region. The vast shelf width in the region has been attributed to the tectonic setting of the region. The shelf narrowed down from the north up to south along the west coast. The width of the shelf along the eastern margin of India also varies from north to south. It is narrow at the southern tip, about 60 kilometers. The continental shelf has a gentle dipping and it attains a depth of about 120 to 140 meter in the shelf break in India. Some shelves are even and have a gentle slope, but some are steep. The seabed of the shelf may vary from rugged, even to rugged. The sedimentation process regulate the ruggedness. A large supply of heterogeneous flux creates an even shelf. The east coast of India has a high concentration of river that discharge an enormous amount of sediment into the shelf. The supply has buried the antecedent hills and channels on the shallow region of the shelf, formed by the biogenic or volcanogenic process. It also has channels of the Pleiora rivers that are now submerged or buried under the modern sediments. Oceanic margin. The oceanic plate occurs at greater than 3000-meter depth. This region is comparatively very young as it formed rather recently at the divergent ocean spreading center by the volcanic process. We know the oceanic plate to be very flat and it has a gradient of 1 is to 10,000. However, some region of the plate has a chain of hills of varying height, and we know this region as mid-oceanic ridge. This is the place where two ocean plates are moving apart. Some hills are several kilometers tall, and some give a chain of island to the ocean. Hawaii is one of the example of oceanic island. The Lakshadweep island of India is another. The Lakshadweep in Iceland of India is another example. These islands were formed during the northward migration of Indian plate after its recent breakup during the early Jurassic period. The trench is the deepest region of the ocean. The Mariana Trench is the deepest region of the world and it is a depth of about 11 kilometers. Origin and evolution of oceanic basin. The age of the earth is about 4.54 billion years. The oldest continental crust on the earth is about 4 billion years. However, you will find in the figure 9.2 that the age of the ocean basin is 200 million years and this age becomes younger over the mid-oceanic ridges. From the foregoing example, it is evident that the land is younger than the earth and oceanic crust is very young. A student may wonder why is there a variation in the age of different rock on the land and the ocean. The age of the continental crust is lesser than the earth because the land mass has formed by cooling of the magma at some later stage. The map of the Encyclopedia Britannica confirms that at the mid-oceanic ridge, a young oceanic plate is forming. This poses a question on the date of the origin of the ocean. Because of degassing of the magma, water molecules have formed over the earth. Dr. Graham Ryder has found sedimentary rocks that have the age of 3.9 billion years, though the age of the igneous rock is found to be about 4 billion. We may infer, therefore, that water was existing on the earth in the initial stage. Considering the quantum of degassing and oldest age of the sedimentary rock, it is also clear that the ocean may have come in existence some 3.9 billion years back. A student of earth science may find it unusual that even though the oceans have formed on the earth in the early stage, no ocean is older than 200 million years. The answer to this riddle lies in the persistent destruction and regeneration of ocean. To understand the generation and destruction of the material of the crust, first we shall briefly grasp some of the fundamentals plate tectonic. The material of the land is made up of shale and is higher compared to the shima. The shale is mostly a continent crust, while the shima is found below the shale on the oceanic crust. The continent, by virtue of a low density, have higher elevation due to isostasy. It may be noted that, as per the plate tectonics, the lithosphere of the Earth may be divided into seven major plate. These plates are African plate, Antarctica plate, Eurasian plate, Indo-Australian plate, North American plate, Pacific plate, and South American plate. Each of these, except the Pacific plate, has oceanic and continental crust. It is believed that arrangement and the geographical distribution of the landmass and the ocean of the globe are regulated by the movement of these plates. We have learned that the crust of Earth consists of oceanic and continental plates. We have also learned that oceanic plates are newly formed regions and are much thinner through the denser than the continental plate. The continental plate are old regions that have been the continent on or the landmass of the globe. From the above description, it is also learned that the ocean crust is very young at the mid-oceanic ridges in the Atlantic Ocean, though it becomes older as it moves away towards the continent. As per the theory of the plate tectonics, it is also known that mantle plumes are deriving from force to move the plates of the lithosphere. At the divergent boundaries, the plumes emanate from the mantle at the mid-oceanic ridge. We have learned in the previous section that the volcanic activities at the mid-oceanic ridge generate new plate and positive bathymetry by accumulating volcanic matter. The edge of the oceanic plate at the mid-oceanic ridges and at the distal location close to the continental rise therefore provide a clue that there is a constant generation of new ocean at the divergent boundary and the newly formed plates move away from the place of origin. The oldest edge of the oceanic plate therefore gives a clue on the time of initiation of formation of the new ocean. However, we have yet to find the answer to the question what has happened to the old ocean. The answer to the riddle is also provided in the plate tectonics. It has been learned that most of the plates are made up of continental and oceanic plate, and these have divergent and convergent boundaries. At the convergent boundary or subduction zone, the plate is consumed as one plate subducts under the other plate. The destruction of the oceanic plate at the subduction zone explains that the oceans are constantly undergoing destruction. The rearrangement of the plate is an ongoing phenomena and it has changed the position of the continent and the ocean several times in the history of the earth. By the rearrangement of the seven plates, individual ocean has expanded or shrunk during the past. Some oceans are now a land mass. For example, the Indian Ocean has formed due to the breakup of a massive land mass known as Gondwana land. The fraction of the Gondwana land with multidirectional drifting of India, the Australia, the Africa, and the American plates has led to the opening of uh, Atlantic, the Pacific, and the Indian Ocean. Southward drifting and rearrangement of a section of the Gondwana land has brought the Antarctica to its present position over the southern pole, and that has led to the formation of the Antarctic Sea. It may also not to be noted that in the present the Atlantic Ocean is widening while the Pacific Ocean is shrinking. Shelf and deep sea sedimentation. As described in the previous section, the sedimentary processes are unique over the shelf as well as over the deep region of the ocean. The shelf, being the extension of the continent over the sea, has a variable environment deposition and sedimentation. Being next to the land, ocean boundary rivers discharge their load into the continental shelf. The erosion of the land by the forces of the sea also contributes to the ocean. The sediments that are supplied into the sea from the land are termed as allogenic. Most of the sediments over the inner shelf are allogenic. These sediments are also called terrigenous. The redistribution of these detritus by the littoral and the shelf current is also very important. Two mode of advection is derived over the shelf. The movement of the detritus parallel to the shore is termed as alongshore. This advection is carried out by the regional or local current. For example, the eastern and the western boundary current in the entire ocean carry detritus is in alongshore direction. The alongshore transport is therefore regional in nature. The other mode of transfer is across shelf movement. This advection carries the sediments from the inner shelf to the deeper region of the ocean. The along-shore winds have a cross-shelf component. These winds generate across-shelf currents. Of the mouth of the river, the plumes of the river are carried for several hundred kilometers. Such plumes carry a considerable amount of suspended matter into the outer shelf by the way of across shelf transfer. The sediments are also carried along or across a shelf in the form of bed load. The direction of such movement depend on the characteristics of the bottom circulation. The resuspension of sediments by a high wind cause a large magnitude of the bed load advection. These sediments are, however, coarser than the sediments that are carried in the seawater as suspension. The movement of sediment at the seabed is by a layer that has a very high density. Besides, detritus on the shelf are also supplied by the wind. Desert and the flood explains of the river have unconsolidated sediments. Wind pick up the sediments from the desert or at the arid plains. Winds laden with the dust are known as dust storm. The dust storm carry a considerable amount of detritus in the tropics. In India, the third desert is known for its dust storm and sediment contribution into sea. Similarly, other deserts also contribute a significant amount of sediments. Because the aerosol dust particle can be sustained in the suspension for longer time in the atmosphere, these are carried in intervention by wind. It may be borne in mind that the winds can supply sediments to a shelf or to a deeper region of ocean. The other source of detritus is to the ocean is through the volcanic activity. The oceans receive sediments through the volcanogenic process at the seabed. It may be borne in the mind that sediments contributed by the volcanogenic process a very coarse grain size, and these are termed as pyroclastic. Clastic. The sediments that are discharged by the volcanoes in the atmosphere are also found to be deposited in the sea. These sediments become a distinct thin layer only in the deeper region of the sea. In the region of high sedimentation, the specific contribution of the volcanogenic process is noticeable only in the vicinity of the coast that has lava flows. The other major source of sediments over the ocean is the autogenic supply. The unicellular organisms live in seawater. Upon their death, the skeleton of these animals is deposited on the seabed. In India, we find very high marine productivity along the SW continental margin of India. The shelf in the region has dominant deposition of remains in the skeleton of the organism. If one looks at the pattern of the sedimentation, the shelf has the several specific features. The inner shelf has a channels filled with sediments. These channels were active when the sea level was lowered. The deep incision of the mouth of the river Indus and the Ganga and Brahmaputra feed deeper fen in the Bay of Bengal and at the Arabian Sea. The outer shelf receives fewer detritus compared to the inner shelf because the across the shelf movement is weaker than alongside advection. The surface of the outer shelf therefore has more roughness because of the deeper water have more productivity because of the upwelling or the presence of reefs. Osteogenic carbonate sediments are found over the outer shelf. In India, the outer shelf is covered with relict carbonate detritus. The continental slope has a much reduced supply of the detritus. The slope of the most of the productivity region has a
What?
high amount of carbonate and organic carbon. Once buried, these deposits are an excellent source of production of petroleum product. The other source of sediments to the slope is through the gravity transfer from the outer shelf. The slumping over the slope is episodic and it is triggered by sea level fluctuation or the slope failure. The gigantic waves, such as tsunami and storm surges, also cause slope failure and slumping in the sea. The continental rise is mostly covered with the thick pile of sediments. These sediments occur in the form of turbidites. The deeper ocean receives very little supply from the land. The sediment's thickness over the oceanic plate is therefore tiny. These sediments are carried over the deeper water in suspension by across self advection. Wind-blown dust and volcanogenic sediments also occur over all the oceanic crust. In the vicinity and mid-oceanic ridges, the pyroclastic sediments are found in abundance. Then physical, chemical, and biological aspect of seawater. Physical aspect. The water in the Western Sea is heavier than the fresh water on the continent. Seawater has a density 103 gram per centimeter cube. The amount of salt, that is salinity, and temperature of seawater regulate its density. The density of seawater varies between 1.02 to 1.5 gram per centimeter cube. The freshwater supply from the river and the melting of the continental and sea ice influence the density of the local water. For example, during the rainy season, a large fluvial discharge of the river into the Bay of Bengal reduces the density of seawater at a regional scale. Evapotranspiration also influences the density. A higher rate of evaporation leads to a loss of water in the form of vapor, and that increases the density of seawater. The density of seawater is crucial for vertical movement of seawater. The ocean has a layered structure. In the ocean, we find lighter density in the mixed layer. The density increases with the depth. The picnon line in the second layer of the ocean, which has a higher density than the surface layer. The deeper region of the ocean have higher density. The vertical variation in the temperature are presented in the figure 4. One finds a top warm layer with uniform temperature. This layer is termed as mixed layer. The water temperature below the mixed layer reduces rapidly with depth. This layer is known as thermocline. The water in the deeper layer also show a reduction in the temperature, but the rate of decrease of temperature in the deeper layer is very low. The temperature of the water is a very important parameter to regulate evaporation and vertical movement of water in the ocean. Associated with a low temperature below the thermocline, the seawater has a high density. This leads to the floating of warm waters and upper surface of a denser cold water. Also, the water is cold near the pole because of prevailing climate. This water has a higher density and it sinks. It also aids the formation of cyclones. Because of high sea surface temperature, the Bay of Bengal has a frequent formation of cyclones. Chemical composition of seawater. The seawater has a thermal conductivity of 0.6 W per mk and at 25 degrees centigrade at a salinity of 35 gram per kg. The pH of the seawater ranges from 7.5 to 8.4. Seawater contains almost all the element. The major constituents of seawater are oxygen, hydrogen, chloride, sodium, magnesium, calcium, potassium, sulfur, and carbon. Sodium chloride, magnesium sulfate, calcium are the most abundant dissolved ion. The salinity of seawater varies between 31 to 36%. The salinity is not uniform. The highest salinity region of the world is the Red Sea. A large influx of the fresh water from the river and from the melting of the ice into the sea reduces its salinity. Sir Edmund Halley was the first researcher to propose the reason for the salinity variation in the sea. He postulated that the proceeds of that continental weathering transported by the river contributes in salt in the sea. The evapotranspiration of sea also increases the salt content. However, recent studies have shown that the contribution of salt, especially that of sodium through the volcanogenic and hydrothermal activity, are also important process that contributes to salinity enhancement of seawater. The solubility of salt in the seawater also depend on the temperature and pressure. In the ocean, the atmospheric pressure increases with depth. Because the temperature of the ocean at the deep level is low, it also increases the dissolution of gases and salts and alters their physical and chemical property. The residence time of various salt in the sea is highly variable. Sodium and chloride have a much longer residence time as compared to calcium. Over the time, the average salinity of the sea has remained same. This has been attributed to three processes. The input of anions and cations estimated to be equal because there is continuous precipitation of salt by chemical as well as biogeochemical process. When seawater moves inland by the tidal forcing or during storm or surges, sodium chloride and calcium sulfate precipitated in warm or arid region of the marginal sea. The rain and Kutch is one of the example where the large amount of sea salt is precipitated due to the cyclic influx of seawater and prevailing warm arid climate. The precipitation associated with the supersaturation of the salt in the sea. Gypsum and carbonate are the salt that are precipitated in the swallow seas. Also, silica and carbon are extracted from the seawater by biogenic process, especially by phytoplankton, the microorganism that fixes these in the presence of sunlight through photosynthesis. Coral, sponges, lobster, and several other living animals, including fish, continuously extract skeleton containing calcium carbonate, phosphate, and several other metals from seawater through primary secondary productivity. Biological characteristics of ocean. The information about the biological character in the ocean water is rather scanty because of the extensive section of the deeper region of the ocean remains virtually unexplored. On the land, primary productivity to a large extent is light limiting and there is well defined food web. On the contrary, in the ocean, only top 100 meter of the water column is prominently sunlit. Yet the entire ocean, including the deep dark regions, is found to have a life. The primary producer in the ocean are of two types, photosynthetic and chemosynthetic. The former are planktons, mostly algae and cyanobacteria, that obtain the energy through photosynthesis. The chemosynthetic community lives in the deeper region of the ocean that does not receive any sunlight. The life here derives its food through the chemical reaction around the thermal plumes emanating from the hydrothermal vents. The trophic level in the ocean are shown in the figure here. The autotrophic communities are generally unicellular phytoplanktonic species that drift in the euphotic zone and produces their food through photosynthesis. It also comprises of some species of macroscopic algae termed as weeds. The depth of euphotic zone depends upon the several factors. Important among these is cloud cover and the turbidity of the sea water. Zooplankton, the floating herbivorous consumer, are heterotrophic, and these occupy the next level of trophic diagram. These organisms vary in size from 2 to 200 micrometer and mostly feed in eutrophic species. Over 1500 species of fungi are known from the marine environment. These are parasitic in on marine algae or animals, or are saprobes in alga, corals, protozoa, sea grasses, wood, and another substrate. The carnivorous consumers of the higher order, fish, squid, and large mammals, occupy the top of the pyramid. Generally, at the each level, only 10% of the energy from the organism is transferred to its consumer. The rest is lost as waste, movement of energy, heat energy, and so on. As a result, each higher trophic level supports a smaller number of organisms. In other words, it has a less biomass. This means that a top level consumer, such as shark, is supported by million of primary producer from the base of the trophic pyramid. So this is about the unit 9. Then we'll move to the next unit. Unit 10. Unit 10 is the ocean current. Ocean is a storehouse of heat, dissolved gases, and almost all the salt and metal present on the earth. It contains about 96% of the sea water. The water constantly remains in motion. The current has a lateral and vertical movement of a water mass and are regulated by thermal gradient, density, and salinity. Waves are a circular movement of water into the no lateral advection of water mass. The waves are important for generating littoral current. The littoral current carries suspended particulate matter along with the shore. Supply of these sediments determines the stability of a coastline. Any man-made structure that obstructs littoral drift may cause erosion of the or deposition along the coast. Ocean currents. The ocean has 96.5% of the water present on the earth. This water is never at rest. Lateral or vertical movement of seawater is prevalent at the surface as well as the depth of ocean. It is termed as ocean current. The currents in the upper surface are more intense because of the air-sea interaction. In shallow region, these are along the shore. In the open ocean, however, currents from the giant higher insolation of the equator turns into the region warmer. The ocean at the polar region, however, remains very cold or frozen. Such a thermal gradient leads to the advection of heat from the equator to the pole. For example, give me 1 second. The surface current are primarily driven by these winds. As the wind prevails over the surface of the ocean, it moves water mass into its direction. Because of the Coriolis force, any poleward movement of water mass gets deflected to its right in the northern hemisphere, and that gives rise to the formation of a giant gyre in the basin. The coastal landmass of continent then channelizes and guides these meridional and zonal advection into regional currents. A poleward advection of water mass is found in the western margin of the globe in the northern hemisphere. These regional currents, many a time, are seasonal. The clockwise western boundary current in the northern region are rapid and warm, and these carry heat from the equator to the pole. Such currents keep the polar regions warm. The equatorward current are found along with the eastern boundary in the northern hemisphere, and these carry cold water. A lack of thermal gradient at a region from the zonal current. At the equator, for example, the winds are easterly and the temperature gradient is rather absent. These winds generate equatorial currents and north and south equatorial counter currents. The circumpolar old current around the Antarctica is another example of zonal current. Upwelling. Upwelling is a process that pumps deeper cold water into the surface from the depth of the ocean. Is an important vertical advection driven by the winds. The winds that prevail at the inclined angle to a shore cause the along-shore advection of coastal water. This process reduces upwelling is an important process that brings nutrients from the depth of ocean. The supply of nutrients from the ocean is a, is a key factor that enhances marine primary productivity and production of oxygen and consumption of CO2 in seawater. Downwelling. The vertical sinking of seawater is also an important process that is regulated by the temperature and density of the sea. From the subtropic to polar region, the surface water cools during winter. The cooling at the poles produces denser water and this sinks to the bottom of the ocean. Such water then move equatorward as bottom current in all the major oceans. These current overturn in the Pacific and the Indian Ocean, making it a convoy or circulation as schematically shown here. The conveyor circulation releases a large amount of heat into the atmosphere from the ocean. This process regulates short and long scale changes in the climate of the globe. Another process that regulates the downwelling is a high rate of evaporation. The removal of water in the vapor from the increased salinity and density of seawater. Water which have a high salinity sink by virtue of their higher density. Downwelling is very prominent in the northern Arabian Sea. During winter, the surface water of the northern region of the Arabian Sea cool. Being denser, these sink. The vertical movement of water leads to the upwelling from the deeper subsurface in the peripheral area. This process is unique to the Arabian Sea and it enhances the marine productivity of the northern Arabian Sea during winter season. Wave property and motion. Wave are surface perturbation in the water mass in which the particle of the medium are displaced in the direction perpendicular to the direction of the energy transport. These perturbations are like the one created in a rope by moving it open and back and forth in the vertical direction. Waves are therefore the manifestation of circular motion of surface water, which is sustained by energy passing through it. During the motion of the wave, there is no lateral movement of water. The main terminology used in describing the wave is wave height, wave length, wave period, wave propagation, and wave stiffness. Classification of the wave. In the ocean, the frictional force created by the wind over the water produces most of the wave. Besides isolated displacement of water by an earthquake, volcano, or slumping with waves, if not obstructed by a margin of continent, waves have potential to travel across the globe. The waves have been classified based on the length, period, and mechanism of their formation. Table 1 describes various types of wave, their typical length period, and the mechanism that regulate their formation. So these are capillary wave, wind wave, sea chain standing wave, and tsunami harbor waves. In tide. Sea wave and swells. We have learned that waves are generated by wind when it blows over a seizable area of the ocean. The wind wave may have a height ranging from slight ripple to 10 meter. Following factors influence the formation of the wind wave. Speed of wind relative to the wave speed. The wind should blow over a large area without significant change in its direction. Width of area affected by fetch. Duration for which the wind has blown over a given fetch and water depth. Disintegration of waves. We have learned that there are region of smaller than half of the wavelength of the wave. Is the as an obstruction of the circular movement of water. This reduces the speed of wave and enhances their height. Disintegration of the wave may therefore start even before these enter the shelf. For example, the western half waves with a wavelength of 400 meter shall be unstable in the region having a water depth of 200 meter. Along the Indian coast, the shelf break occur between the depth 100 to 130 meter. Any wave that has a length less than 360 meter shall retard from the Indian shelf. Because of the continental slope has much steeper gradient than the continental shelf, this effect is stronger over the slope region. There are several hills and basins on the shelf and in the inland region. It has been learned that the speed of the wave in the shallow region is regulated by the water depth. This implies that speed of the wave shall be more in the basins compared to the mount of the hill. On the continental, uh, give me 1 minute, please. I'll be back. So there are several hills and basins on the shelf and in the inland region. It has been learned that the speed of the wave in the shallow region is regulated by the water depth. This implies that the speed of the wave shall be more in the basin compared to over a mound of hill. On the continental shelf, that is a variable bathymetry, there will be a complex variation in the speed and height. Such variation lead to a refraction of the wave over the shelf. Littoral current. Wave break at the shore because of the disintegration of the wave. A great majority of the breakers result from the process and it generates littoral current. Littoral current is an along-shore advection of seawater. The current direction of these is regulated by the direction of the waves. It has been described in the previous section that the direction of the wave is regulated by the wind. In most of the oceanic basin, the direction of the wind is highly seasonal. For India, the speed of wind is manifold higher during the southwest monsoon, and their direction is from southwest, west, and southeast. Winds are milder and the direction reverses after the southwest monsoon. The wave climate is therefore the completely differing during the each season. Is in response to the wind climate, longer and higher wave from southwest to southeast prevail during the southwest monsoon. These waves generate a strong littoral current. Tsunami. The wave of the harbor at the most destructive, very large solitary wave. These cause inland induction and the destruction of coastal establishment for several kilometers. These have a wavelength ranging from 10 km to several hundred km and have a very long period. Unlike the storm surges, tsunamis are not produced by wind. These waves are caused by a vertical displacement of water of ocean by an earthquake, a large slumping, or by an eruption of the volcano on the oceanic floor. The tsunami are therefore produced by the process at the bottom of the sea floor. For example, the tsunami that struck the east coast of the India on 26 December 2004 was formed several hundred kilometers away by an earthquake in the subduction zone at a converging plate boundary in the deep ocean. Tsunamis have very low amplitude in the deeper region, and therefore these travel a long distance is in all direction from the epicenter of the origin unnoticed. However, when these arrive in the coastal water, the shallow depth of a shelf induces enormous amplification in their height. The occurrence of tsunami is an episodic phenomena and it continues till the energy of this wave is fully dissipated. Considering a large destruction by this wave, Government of India has installed a tsunami warning system in the ocean. Tide. Tide are semi-diurnal or diurnal cyclic changes at the sea level. Tidal waves are generated because of the gravitational pull of the sun and the moon. As per the Newton's law, a gravitational attraction between two bodies is proportional to the product of the masses of the two bodies and inversely proportional to the square of the distance between the two. This implies that the bodies with the greater mass and close to each other shall produce a stronger attraction. Despite smaller size, therefore the moon and has a twofold higher gravitational pull on the earth. This pull induces two bulges at the equator and it produces an enormous wave with low amplitude. To further understand the process, let us assume that the earth is fully covered with water and no land mass. In such scenario, water from the pole will migrate to the equator to create a tidal bulge every 12 hours due to gravitational pull of the moon. The tidal wave from the wave will then propagate around the earth. However, the earth is not fully covered with water and it has continent which restrict the free passage of tide. We will describe the role of the obstruction in the later part of the section. While the Earth is rotating on its axis 24 hours, the Moon is also revolving around the Earth. The direction of the revolving of the Moon and the Earth is the same. In order to complete one lunar day, therefore, Earth has moved a bit more. The Earth takes 24 hour plus 1 by 29.5 day or 24 hour and 50 minute. Lunar day is therefore a longer than a solar day. Because of this, every solar day, the time of high and low tide has an increment of 50 minutes. Classification of tide. Because of the moon takes about 24 hour 50 minutes to revolve around the earth, there theoretically there shall be a 12-hour 25-minute cycle changes in the water level associated with the attraction of moon. Such a tidal cycle is called a diurnal cycle. The term ebb is used during the low water, while the high water level is called a flood tide. If the earth was moving having no land mass, the bulge of water produced by the moon would have diurnal changes at all the point of the earth. However, because of the obstruction in the passage of the tidal wave by the continents, there is a large variation in the tidal cycle. Many regions have too low and high tides every day. These tides are called semi-diurnal. ARC exchange. Air-water interface is the layer in which ocean and atmosphere interact. It is of the paramount importance because at this interface, the transfer of energy, heat, vapor, gas, and ions take place between atmosphere and ocean. The characteristics of this interference determine the quantum of gaseous flux. evaporation rate, and sinking of heat in the ocean water or its advection from the ocean into the atmosphere. So here is the parameter density, specific heat, seawater and air has been compared. ARC exchange. The parameters that are important and contribute to ARC exchange are solar radiation, air temperature, sea surface temperature, variation in the scalar winds, humidity, atmospheric pressure, surface salinity, and clouds cover. The role of this parameter on air water exchange, air sea exchange is described below. Solar radiation absorption, reflection, scattering. The amount of solar radiation received on Earth differs. It depends on duration and the angle of ray in the sun. And the solar constant S0 is the amount of solar radiation received at the top of the atmosphere. It is 1378 W per meter square. All the energy does not reach the Earth. The absorption, reflection, and back reflection are the process that regulate the solar budget of the Earth. It is given in the figure 10.13. The figure suggests that out of 100 units received at TOA, 30% radiation is reflected by backscattering on the molecule of gases, by cloud 20%, and by surface of earth is 4%. The amount of reflection is highly variable and uncertain because of the cloud cover is seasonal and highly dynamic. The characteristics of the surface also determine reflection. The trees have much reduced albedo than the ocean. Glaciers have very high albedo. Incoming solar radiation is also absorbed before it reaches the surface of the Earth. It has been estimated that 19% of the insolation absorbed, 16% by greenhouse, CO2, methane, and water vapor, and 3% by cloud. Therefore, only 51% of the total solar insolation received at the TOA reaches the Earth. It may be noted that this amount is not uniform over the globe. The greenhouse gases play a vital role. We all know that the concentration of greenhouse gases is increasing in the atmosphere because of the anthropogenic activity, and that is an enhanced absorption of solar insolation in the atmosphere. Seasonal clouds cover also influence the amount of solar radiation insolation over a region. In India, there is an intense cloud cover during the southwest monsoon. It reduces the influx of solar radiation during June September. Figure 10.14 provides quantum the energy of the different systems over the globe that take part in air sea exchange process. Evaporation. Evaporation of seawater also consumes solar energy and it enhances transfer of latent heat into the ocean. The equatorial region of the earth always receives sunlight with no seasonality and heat hits the ocean. The amount of evaporation and latent heat flux into the atmosphere therefore maximum in the equatorial region. The trade wind which are warm over the equator pick up an enormous amount of vapor from the sea at the air sea interface. The poles are cold and have colder winds and sea surface temperature. The amount of evaporation therefore insubstantial in the polar and subpolar region. Precipitation. The vapor exchange at the air-sea interface condense and precipitates. Higher sea surface temperature of tropical ocean induces high evaporation and precipitation. Rising air parcel over the equator carry latent heat from the ocean into the atmosphere. Rising air undergoes adiabatic cooling, which causes heavy rainfall or release of latent heat in the atmosphere. In the Bay of Bengal, it is found that higher sea surface temperature breeds to low pressures or cyclone. The cyclone transfer a vast amount of latent heat from the ocean into the atmosphere. The cyclone releases latent heat through the precipitation over the continent. Ocean over the wave generation decay. The ocean waves are another player in an sea exchange. The wind that generate the wave also transport the wind stress. As described in the earlier section, wind carry the energy. The circular movement of water leads to the downward advection of heat. You have learned that the length of the wave determines the depth of the circular movement. It implies that larger wave induces deeper mixing. Vertical mixing increases the depth of the mixed layer or storage space within the upper layer in the basin. Propagation of the wave also moves kinetic energy from a deeper region to the shore. The decay of the wave also releases an enormous amount of kinetic energy. All this process aid in higher ARC interaction. Then ion exchange. The solar energy regulates the ion exchange between the ARC. The exchange of the ions of hydrogen and oxygen is the most prominent. Ion exchange also carries out fractionation of isotopes. Vapors has a higher amount of lighter isotope compared to the seawater. Similarly, vapor also contains fewer salt. These processes have selectively enriched ocean in salt and heavier isotopes. The breaking of the wave also helped the exchange of salt between the ocean and the atmosphere in the form of aerosol. We have learned that breaking of the wave creates white caps. These caps have uh, many bubbles which rise to the surface. These bubbles produce a large flux of aerosols which are sprayed into the air. Production of aerosols have been also been reported in the deep sea during the cyclonic depression. High waves spray seawater that carries particular particles from the sea to atmosphere. These aerosols act as a nucleus around which the water particle condense in the air column. Gas exchange in the water interface, seawater interface. The transfer of gases between the ocean and the atmosphere takes place by the difference in the concentration of the gases in water and the air exchange rate. To remove the disequilibrium in the concentration of the gases between these two components. To understand the dissolution of the gas and ocean, we should know the concentration of gas in the atmosphere. We have nitrogen, oxygen, argon, CO2, neon. The ARC exchange is also regulated by thermal diffusion and irreversible thermodynamics. For sake of simplicity, we learn the basic principle that regulate the exchange of gases at the sea level. Besides the partial pressure of gas, the temperature of the water mass also determines the solubility. Colder water has a higher dissolution of the gases. As the temperature of seawater increases, it keeps a less amount of gases. In the global warming scenario, the sea surface temperature is expected to increase. This will lead to a reduced dissolution of gases. Some expert expects a massive degassing of the ocean because of global warming. We must, however, remember that dissolution of gases in the seawater is also regulated by the salinity. So this is the end of the block unit 10. Then we will go to unit 11, that is hydrology. Distribution of water in the crust. Ocean stores 96.5% of the globe. The extra evapotranspiration of the ocean contributes vapor to the atmosphere. The condensation vapor in the form of ice or rain supplies fresh water. The distribution of water on the globe is shown schematically in the figure. We may note that out of the 3.5% of water present in the land, only 2.5% is fresh water. Many of the large inland water bodies, such as the Caspian Sea or the Aral Sea, are saline. Saline water comprises 0.9% of the water. Surface distribution. The water unevenly distributed over the globe. It is stored in river, atmosphere, living mammals, animals, plants, swamps, marshes, soil moisture, Lake, ground ice, and permafrost, glaciers, and ice caps are the major storehouse of fresh water. The seasonal melting of these regulates runoff of most of these major rivers of the world. A part of this water also preserved as groundwater. Here, we shall remember that most groundwater is also fresh water, but it is not considered as surface water. Surface distribution. We remember that formation of water on the earth has been associated with the degassing at the crust and the mantle. It is an ongoing process. The water has a long history to be stored in the subsurface of the earth. It becomes relevant, therefore, to evaluate mode of occurrence of water in deeper subsurface crust. In the term groundwater refers to the water present in the crust in all the physical state, in the sedimentary as well as the massive crystallized rock. It is not part of the surface water as it occurs in the subsurface. Groundwater stores about 1.7% of the total water in the globe. About 30.1% of the fresh water on the earth occurs as groundwater. About 23.4 million of cubic kilometer water is stored as groundwater. There exists no estimation of the amount of water present as juvenile or sedimentogenic water and the advection pathway in the deeper surface of the crust. The subsurface occurrence of the groundwater has been divided into two classes. The upper zone is known as the zone of aeration. In this zone, voids are partially filled with water and air. Below the zone of saturation is present. In this zone, all voids are filled with water. This water may be again the category as hydroscopic, capillary, and gravitational water. Hydroscopic water is mostly contributed by the absorption from the air. This is found in the form of thin film on soil particles and is regulated by environmental parameters. The temperature and the relative humidity are the two parameters that control the absorption of this water. Capillary water is held by surface tension in the region that has atmospheric pressure. This water has a continuous film. This water forms a continuous film and it can be used by the biosphere. Gravitational water is also found in the aerated zone that has hydraulic pressure. This water is different as it is not retained by capillary and hygroscopic process. It can be drained from the soil under the force of gravity and is contributed into the deeper layer of the soil. Intermediate water in some horizons occurs below the capillary water. The sediment and distinction of the water is not clear. In the saturation zone of the crust, water is retained under the hydraulic pressure and it lies between the capillary zone and the impermeable layer. The hydraulic pressure is always more than 1 atmosphere here. The vertical extent of saturation zone is shown schematically in the figure given below. Please note that if there is no impermeable layer above the saturation zone shall lie between the water table and the impermeable rock. You shall also remember that the hydraulic pressure in the saturation zone determines the position of the water table. If we ignore the capillary attraction in the upper surface of the subtraction zone, the level of water shall lie at the layer that has atmospheric hydraulic pressure. According to the condition of their occurrence, the subsurface water can be called as free gravitational, solid state, vapor, physically or chemically bound, and in supercritical state. The free gravitational water is found in the pore, fractures, and in voids. We have learned that this water percolates into the formation under the pressure gradient. It may be noted that any formation can be classified according to the ability to store water. These may be called as water bearing, water permeable, and water impermeable. Hydrologic cycle. The exchange of water among different reservoirs of the globe is known as hydrological cycle. The component of hydrological reservoirs are ocean, atmosphere, groundwater, runoff from the land, the insolation of the prime force that drives the hydrological cycle. Heat supplied by the sun regulates the evaporation of water bodies. Water vapor is contributed into atmosphere by wind. Because of the adiabatic expansion of gases, air masses cools by vertical advection into atmosphere. This process leads to condensation of water vapor around aerosol. Water is carried around the globe by winds till it gets precipitated as snow or rain. The atmosphere is the only reservoir in which water is present as water, ice, and vapor. The water that falls as snow preserves as glaciers and ice caps. Rainwater is stored in lake and the swamps, rivers, etc. Rainwater also gets stored in the subsurface as groundwater. Runoff is the mechanism that transports the stored water on the land into ocean or large water bodies. Have you noticed that a river carried water contributed from the rain, glacier, or lake for a long distance and it finally reaches the sea? During the cycle, some amount of runoff gets evaporated in the tropical region and that contributes vapor to the atmosphere. The cyclic journey of the water among the ocean, atmosphere, land, ocean, or large inland water bodies is known as water cycle or hydrological cycle. Then genetic type of groundwater. We know that the degassing of the earth during the early stage and of cooling has released water and created a hydrosphere over the globe. Some hydrologists such as V.I. and Bernardeschi therefore thought water is a mineral. The genetic classification of the water was therefore introduced in the hydrology. You may be reminded that there are two major sources of water in the crust. We know that the downward percolation of water is a major source of groundwater. We are less familiar that some amount of water is also contributed because of deep seated process that release water at the crust. Mental boundary. The water is known as Jubilian water. The amount of water contributed from the process is tiny. Therefore, the earth is receiving water from this process for the past several billion years. It may be noted here that almost all the water present in the globe has originated because of this process. Based on this movement, genetic classification of water has been made. The terms exogenic and endogenic are coined to classify these waters. The exogenic water percolates downward into the crust. The endogenic water, however, percolates upward. Based upon the mode of formation, water have been divided into four major types, that is infiltrogenic, sedimentogenic, metamorphogenic, and magmatogenic. It may be noted here that type 1 and type 2 falls under exogenic category, that is infiltrogenic and sedimentogenic, while type 3 and type 4 are fall under endogenic category, that is metamorphogenic and magmatogenic. Then first one is infiltrogenic water. This water is almost contributed from the precipitation. One is not aware that some water also moves in the form of water vapor within. Based on the process of its contribution, water in the crust is subdivided into percolating, condensing water. The condensation of the water and vapor in the crust for produced condensing water. Depending on the source, mode of supply, and salinity, infiltrogenic water may also be subdivided into meteoric and thalsogenic water. Given below a detailed description of the different kind of water. So groundwater is two types: exogenic, endogenic. Exogenic is two type: infiltrogenic and sedimentogenic. Endogenic is two type: metamorphogenic and magmatogenic. Then infiltrogenic and again divided into two types. Sedimentogenic again divided into two types. So the division is shown in this figure, and the genetic classification of water. Then comes residence time of water. We have learned that The age of water in any reservoir is regulated by the amount of water or rate of supply of loss. It is therefore important for us to understand that the magnitude of water in the each of the subsurface reservoirs. We have discussed the residence time of water in atmosphere, ice caps, glaciers, rivers, and in the ocean. We shall now discuss the residence time of the infiltrogenic water in the crust. At first glance, we find that soil water has least residence time, 2 weeks to 1 year. Because capillary water is used by the plant, its residence time is also noticeably short. The residence time of atomogenic water is the lake is highly variable. The lake in the tropical region fill during the rainy season and get dried up during the summer. The residence time of most of the medium-sized lake is therefore very small. The lake of the higher altitude have twin source of water supply. Water into these lakes is contributed from the melting of ice and from the rain. We have already discussed the residence time of water in river system. Even though the amount of rainfall in one of the contributing factor in the pluvial flux, it is not controlling parameter in the residence time of the water in the reservoirs. In the rivers, the groundwater has a highly variable residence time. Hydrologists estimate their residence time by T1. T1 is the average time elapsed between the recharge and the discharge of groundwater. The resident time of water in a reservoir regulated by its recharge rate, size, depth, and withdrawal from it. In the larger aquifer, the water has been much longer residence time, while for small isolated aquifers it is short. Resident time from 25 to 3 to 30 kilo years for deep-seated aquifers. Sedimentogenic water has also a very large residence time. The water preserved in the sedimentary rock is tied in the minerals. Its extraction therefore takes place during the process of metamorphism. The residence time for the metamorphosing water is large. The residence time for the magmontogenic waters appears to be very large, as they are mostly produced as the mantle and the crust boundary. In the spreading center of the earth, the mantle plume carrying this water descends. The water may be syngentic or epigentic. Syngentic water has a large residence time. Then type of aquifers. An aquifer is defined as an underground water bearing formation. In the crust, four types of aquifers are found: unconfined, purged, confined, and leaky. So here is the type of aquifer the diagram shows: the purged aquifer, the leaky aquifer. Then spring and the classification. Spring is a natural formation in which water from the deep subsurface flows on the surface of the earth, creating visible flow. And the basic principle that governs this flow is the position of hydraulic head or pressure head in a confined aquifer. The spring also form above the level of the unconfined aquifer is the water table intersect in the ground. For being classified as spring, the water flow on the surface should be regulated by the pressure within an aquifer. Classification of spring. The classification based on temperature, classification based on flow, classification based on geomorphological control. So for today, I will stop it here. I have some other works somewhere to go. So we'll again meet some other day. Thank you.
Okay, sir.